We're now going to talk about the central Calculus 1 concept, the derivative. And we're going to ask the question, how do we define the slope for a curve? You are familiar with these three ways of characterizing the slope of a line, that it is the rise over the run, calculated by finding the rise over the run, y2 minus y1 over x2 minus x1, or delta y over delta x, which is change in y over change in x. So let's start with those definitions for the slope of a line and build a definition for the slope of a curve. So if we use the y2 minus y1 over x2 minus x1 definition of the slope for a line for a curve, let's see what happens. Here's our y2, here's our y1, here's our x2, and here's our x1, and we get this attempt at a definition for the slope of a curve. But we see in looking at this slope right here that it doesn't make sense to call it the slope of the line at this point, because we want to think of the slope of the line as giving us the direction the curve is pointing if we are moving along the curve at that point, and then we stop. So if we use arrows to point at the direction we're moving along a curve, we're moving down here, down and a little more to the right here, and by the time we get to this point we should be moving in this direction to define the slope of the curve, and clearly this attempt at our definition isn't moving in the right direction. So how do we fix that? So what we're going to do is move this second point x plus h closer to the first point x and see if that helps us get a more accurate slope for the curve, and actually find the slope for the curve. So we've done this once and we see that it's a little better, but still not what it should be. Let's do it once more. So we've done this once more. The x plus h has moved even closer to x, but still not pointing in the right direction. So let's do it once more. Okay, so at this point we've got it. This secant slope right here in the red line actually is the slope of the curve. It's pointing in the direction that it should, in this direction. But what has happened is that the x plus h has moved all the way over to x. And so instead of our denominator being x plus h minus h, we've actually moved all the way to x. If we write that formally, mathematically, what we have is this, that we've taken the limit as h goes to 0 of f of x plus h minus f of x over h. On the next slide, let's summarize what we've done. So we first tried to get the slope of a line using, or the slope of a curve using the definition of a slope of a line, using the rise over run definition. That turned out to give us a secant slope, and we saw on the previous slide that those were inaccurate slopes. But as we let our h value go to 0, we found that we got the slope we wanted, which was the tangent slope. So let's characterize these two different slopes in a slightly different way. We're going to call those secant slopes approximate slopes, and the tangent slope is an exact slope. So if we go back to the previous slide, we see that these secant slopes right here this one was very inaccurate as a guess for the slope of the curve. This one was a little bit better, but still far off. This one was a little bit better, but the tangent slope gave us what we wanted. It pointed in the correct direction. And how we got there was by letting x plus h go all the way to x. So we're actually dividing by 0. So we're going to note that the tangent slope is a 0 over 0 slope, and that's why we spent so much time talking about 0 over 0 slopes in the previous chapter, because the slope of a curve is a 0 over 0 slope. So let's summarize what we have in words now. So the slope of a curve is defined as the limit as h goes to 0 of the approximating secant slopes, these slopes, and that is written as, so that is this slope here, and that is the tangent slope. So again, graphically, we wind up with the slope of the curve being its tangent, this red slope, and that is this limit of the rise over the run. So secants give approximate slopes, and the tangent is the exact slope of the curve. In our next video, we are going to apply this new definition to a function, and we'll be able to see that this limit definition of the derivative actually does give us the slope of the curve at several points that we're going to examine.